While you're watching this video, likely in the warm indoors, I will probably be shivering in a tent out on the Ross Ice Shelf, the largest ice shelf in Antarctica. I'm surrounded by a team of 6 other scientists, engineers, and mountaineers, and we're all crammed into a single 4-wall tent, surrounded by scientific equipment, cold weather gear, as well as cooking supplies and food. We will spend the next 3 weeks living together in one of the harshest environments on Earth. The average temperature around this time is negative 30 degrees Celsius, or negative 22 degrees Fahrenheit, although with our stove creating heat, it's just above freezing in our tent. While here, we will likely encounter harsh winds that can pick up to 50 miles per hour and sometimes worse, and 24-hour days of intense sunlight that reflects off the barren ice. So how exactly did we get here, and why are we in such a harsh and remote environment? Our mission is to perform a scientific study of the Ross Ice Shelf and determine how stable it will be in the future. If you don't already have ideas, you're probably wondering, what does the Ross Ice Shelf have to do with sea level rise? It plays an important role in controlling the amount of ice that is added to the ocean. Much of what we know comes from looking into the past at a different ice shelf, the Larsen B ice shelf in the Antarctic Peninsula. In 2002, Larsen B made major headlines as the ice shelf disintegrated rapidly over a few months. Studying the effects of its collapse can shed many insights into Ross Ice Shelf stability. The first thing we should note is that the collapse of the Larsen B ice shelf did not directly contribute to sea level rise, like we might expect. To better understand this, let's observe what happens when several ice cubes melt in water. First, we will add water and a few ice cubes to a glass and fill the glass to the brim. Notice that the ice cubes float above the top of the glass. In this model, the ocean is represented by the water, and the ice cubes represent an ice shelf like the Ross or Larsen B. Now, the question we want to answer is, what will happen to the water level as the ice melts? Let's make a prediction. Will the water level stay the same? Will it become lower? Or will it rise and overflow? Let's observe for ourselves. Notice that the water level remains exactly the same as the ice melts. This is similar to what happened in the collapse of the Larsen B and what would happen if Ross collapsed. Alright, so if an ice shelf breaking up doesn't directly contribute to sea level rise, what's the connection? Let's go back to the case of Larsen B. Following its breakup, the glaciers feeding into the ice shelf underwent a significant acceleration, speeding up and causing 33% more ice to be emptied into the ocean. So why did the glaciers feeding the Larsen B ice shelf suddenly accelerate following its collapse? Well, ice shelves act like a dam in that they push back against the glaciers that feed into them. Imagine what would happen if all of a sudden the Hoover Dam disappeared. Without the dam holding the water back, the lake above would suddenly fill the valleys because nothing would be holding it back. The same effect occurred following the Larsen B collapse. All ice shelves hold back the glaciers that feed into them from land, and their acceleration leads into an increase in the amount of ice emptied into the ocean, and will result in sea level rise. Now let's take a moment to revisit the purpose of studying the Ross Ice Shelf. In all topics studied by scientists, the scientific process involves answering questions through investigations. So what questions am I trying to address, and where do I start? As I mentioned before, I want to know how the Ross Ice Shelf is changing. This is important to better understand eventual sea level rise from new ice being added to the ocean, just like we observed after the collapse of the Larsen B. Our observations of past events like this can help us focus our questions on things that we actually test and measure. While no one's predicting that the Ross Ice Shelf is going to collapse anytime soon, scientists are beginning to observe changes along the sides of the ice shelf. And this could have implications on how it's able to provide force pushing back the glaciers that feed into it. We need to develop a set of research questions to guide our investigation and focus our attention on changes in the Ross Ice Shelf that we can measure to make predictions. Here are a few of the research questions I hope to address. Is the Ross Ice Shelf speeding up or changing its flow pattern? Are there indications of crevassing within the ice that could tell us more about the stability of the ice shelf? What areas of the Ross Ice Shelf are most important in maintaining its ability to push back on the glaciers that feed into it? By making observations and gathering data from the Ross Ice Shelf, we hope to be able to answer questions about the role ice shelves play in future sea level rise. In the next video, we'll make decisions about what information we need to collect from the Ross Ice Shelf to answer those research questions. Can you think of some data sets that you would collect to help answer our questions? How would you collect those data sets? Thanks for following, and I'll see you next time.